isn't very interesting when the terms all make clearly sense. As I explained to you, when there's no problem interpreting the terms, the formula is satisfied by big margins, so it doesn't seem very interesting. Now, Cassini defined the terms in a way that makes it interesting, and also true. Now, to underscore how far Cassini's interpretation is from classical formulas, let me point out that it's possible for both sides to be negative. But even though both sides can be negative, the inequality is still true, because it's a universal statement of positivity of relative entropy. The fact that the left-hand side can be negative is something, it's a special case of what we've already proved. We proved at least 6 weeks ago, I think, that any smearing of the energy in a region that's small enough that it's space-like separated from another region gives an operator that's not positive definite. Right? The way we proved it, we first proved that such an operator can't annihilate the vacuum. That's the Riesz-Leiter theorem. And then we showed that the vacuum plus some constant times this thing acting on the vacuum sorry. Let me say it better. The vacuum plus some constant times a state that has a non-zero since the operator doesn't annihilate the vacuum, we can pick a state with the non-zero inner product, a non-zero matrix element of the operator from the vacuum. And then we showed that if we take a suitable linear combination, we get a state where the left-hand side is negative. So that's how we prove that the energy density itself can't be positive definite. And smeared over any region that's space-like separated from another region, it's still not positive. So the left-hand side isn't positive. By the way, the reason I caught myself, and I didn't put in this state itself, but some state with which this has a non-zero inner product, is that this state would not be a Hilbert space state. Remember that K right, this thing, is not an operator. It takes the vacuum out of Hilbert space. But nevertheless, it has well-defined matrix elements. So in the correct version of the proof I started to give, we consider not the state gotten by this thing acting on the vacuum itself. That's not a Hilbert space state. We take any Hilbert space state with which this operator has a non-zero matrix element from the vacuum. So it really shows how non-classical the statement is, that both the left and right-hand side can be negative. Now, is there anything else I wanted to say about the Bekenstein bound? No. Well, one other lesson we learned is that although Bekenstein had intended thermodynamic entropy as S, we learned in the example of the Bekenstein bound that S has to be interpreted as von Neumann entropy. And that's a lesson that will carry over in the later examples we'll discuss related to black hole thermodynamics. So that's all I'll say by way of after action, filling in details on the Bekenstein bound, unless there are questions. Okay. Now, on the monotonicity of relative entropy under expanding a region, there was a point I didn't explain well. So we had this operator TV that went from H to H plus H bar that takes X to X plus Sx. And then we had pi v, which is supposed to be the projector on TV of H, which I think I called kV. And then I claimed the formula that pi v was TV 1 over TV dagger TV. TV dagger. I didn't quite prove that this formula was correct. I only proved that pi v projected onto a subspace of kV. To prove it projects onto all of kV, I just had to say the following. If we make this operator act on a state which is in the image of pi v, which means a state of the form, in the image of TV, meaning a state of the form tvx, you immediately, if you write the daggers in the right place, you immediately see that everything cancels out. And this is TVX. So what I called pi v does indeed have in its image all of TV. Oh, sorry. The image of pi v is, first of all, consists only of the states of the form TV times something, but it includes all states of the form TV times something. So, anyway, we also explained last time that TV was Hermitian, and it follows from what I've said now that it squares itself. So that's what I wish I would have said when we were talking about relative monotonicity of relative entropy. As was also pointed out after the class by one of you, after developing various methods, we then are proceeding to 3 applications. One we did yesterday, which was the Bekenstein bound, and today we'll do the C theorem and the ANAC. It was correctly pointed out that this used only positivity of relative entropy. The other 2 will actually use the deeper property of monotonicity. For the ANAC, we'll use monotonicity in exactly the form we proved on Tuesday. For the C theorem, we're instead going to use strong subadditivity, which, as we've discussed, is a corollary of monotonicity of relative entropy. But it's not exactly the statement we proved Tuesday. But more importantly, for the ANAC, we're actually going to literally use monotonicity in exactly the form we proved Tuesday, under enlarging a region. But for the C theorem, we're going to use the fact that strong subadditivity holds in general quantum mechanics, which we didn't quite prove. I merely told you that if you want to look in, well, I merely told you that it's possible to imitate the proof we gave for a general quantum system, but I didn't present that in the class. As I remarked, it is in one of my sets of lecture notes. Okay, those of you who are just coming in missed some filling in of after-action details from Tuesday. But we're now starting a new topic, which will be the C theorem. So what is the C theorem? This has to do with the following question. Is renormalization group flow irreversible? So intuitively, in Wilson's description of the renormalization group, what you're doing is integrating out high energy degrees of freedom to produce an effective theory at lower energies. And since you have integrated out some degrees of freedom, it sounds like it should be irreversible. From the point of view of the perturbative renormalization group, that's less obvious. There you look at equations like you have couplings G alpha. You look at equations like, perturbatively, you define a vector field in the space of renormalizable couplings, and then you could ask, could that vector field be such that there are orbits that are closed loops? That was a question when I was a graduate student, and it was certainly an unanswered question at that time. The first proof was by Zamolodchikov. So this was in 2 dimensions. Zamolodchikov manipulated the 2-point function of the stress tensor and proved that a certain linear combinations of 2-point functions of stress tensor components was monotonic under renormalization group flow. So he defined a C function that equals the usual C at a fixed point. That means 4 is a conformal field theory. And then he showed that the renormalization group flow can only decrease C. and dc dt strictly negative except for a CFT in Zamolodchikov's work. So a CFT corresponds to the case that the RG flow is trivial. That's not a non-trivial closed loop. And for anything except a CFT, Zamolodchikov proved that there's a function C on the space of all quantum field theories that decreases along all non-trivial RG flows. So he proved that in 2 dimensions, at least for relativistic theories, the RG flow is irreversible. However, well, that proof is great, but it's not what we're going to present today. Cassini and Witten around 2007 gave a new proof that uses this sort of tools we've been developing, and that's the proof that I'll explain. And this was, again, in 2 dimensions. The Zamolodchikov proof was adapted to 4 dimensions later. And likewise, the Cassini-Witten proof was extended to both 3 and 4 dimensions in later papers by Cassini and various co-authors. But I'm only going to present the version in 2 dimensions. The version in 3 dimensions really is a more complicated application of the same ideas. And the version in 4 dimensions does involve a new idea, which is what we'll explain when we get to the ANIC. But I'm not going to then go back to explain the 4-dimensional version of this proof. The 2-dimensional version is as follows. First, we pick light cone coordinates on 2D Minkowski space. And then we consider the future light cone of a point. And let me arrange my coordinates so they go like so. And I pick some points on the future light cone of a point. 2 points on each null ray that goes into the future. Then we connect them up. And now I'm going to give names to the various regions we've drawn. So this will be region A, this is region C, this is region B, and this is region A, B, C. And now we're going to use strong subadditivity. Well, so each of A, B, so strong subadditivity says that SAB plus SBC is equal to or bigger than SB plus SABC. Now, for example, in this formula, ABC is an interval. And when we talk about the entropy in an interval, that's equivalent to talking about the entropy in the causal diamond of the interval. So we define a space, each interval defines a space-time region. So if we take ABC, the space-time region would be given by this diamond. If I take AB, AB would be given by this diagonal. Well, it would have a different diamond, which I'm reluctant to draw because the picture would become too busy. But in your mind's eye, imagine starting with these 2 points and then constructing the domain of dependence by emitting light rays to the future and past that go in my picture at pi/2 angles from the vertical. So that one would be something like this. And similarly for this one and this one. So we discussed the entropy associated to an interval. Remember that in a CFT, if you have an interval I, let's say, of length L, the entropy was C/3 times the log of L over a UV cutoff epsilon. An interesting thing you'll notice about this inequality is that the UV cutoff cancels out. Because The coefficient with which the epsilon appears is independent of L, independent of the length of the interval. And in this inequality, we have the same number of entropies on each side. So whatever the UV divergent part is, it cancels out among these formulas. So from a pragmatic point of view as a physicist, this inequality makes perfect sense. The difference between the left and right-hand sides is cutoff independent. Mathematically, it's not really understood because the individual entropies weren't well defined since they were ultraviolet divergent. In a cutoff theory, they would be well defined and strong subadditivity would be rigorous. But in a cutoff theory, some of our other steps wouldn't work. So I'm going to be presenting an argument which I think is extremely convincing from a physical point of view, but it's definitely not understood rigorously mathematically. All we're going to do then is to work out the consequences of this formula. So with this metric, the distance from uv to u prime v prime is I don't like the minus sign. Maybe there's no minus sign with the way. Oh. I'm actually unhappy about the sign, so if nobody wants to help me out, I'm going to just proceed. So I'm going to call I'm giving names to the positions of these coordinates, v1, v2, and u1, u2. And then b, there's a square root here. b would have length square root of square root of u1, v1. ABC is the square root of u2, v2. And the others, so AB is over here. So I got the square root of u2, v1. And C is the square root of u1, v2. So we just want to implement this formula with these values of the lengths. We'll specialize more by taking u1, v1 equals r. u1 equals v1 equals r. And u2 equals v2 equals r prime. So
is B supposed to be a spatial slice?
B?
Yeah, because if B is a spatial slice, it seems to me that the length should be just v minus u instead of the square root.
Oh,
Because when you have the u and the v are in the same point.
oh gosh. Well, let's try it your way and see what happens. I can't argue with that. No, sorry. Well, it's only a spatial slice if u equals v. this is a little bit embarrassing, I'm afraid, but let's, okay.
But like the sign cancels, right? Because you're like subtracting. So one part is like U coming out, and the other is not, and V is
Yeah.
subtracted, and then you get a minus, right? Cancel the minus, and that's it.
So what should I have then for this?
I think that's right, right?
Well, one point is here, maybe with the square root of 2. The other point is here. Oh, sorry. One point is tx's are both equal to u. The other one has a minus sign. We have something like this for the 2 points, right? So then we have to take t1 minus t2 and x1 minus x2. One has a plus sign. Okay. So we're going to get u plus v. Is that what you're recommending? Okay. Well, we actually are going to specialize in the case where u1 and v1 are equal. So there are. And then, as the questioner was suggesting, the distances are here. And this one is r prime. And the other ones are the square root of r prime. I'm sorry to get confused here, but I'm pretty sure that those formulas are correct. Since I've messed up a bit, though, I really better invite you all to ask questions. Well, I've messed up the explanation a bit, but I'm pretty sure that those formulas for the lengths are correct. So what we get then is 2 times s of the square root of r prime is equal to or greater than s of r plus s of r prime. So now we just expand this in, well, what can you learn from it? To learn something from it, you let r prime equals r plus a, and just expand for small a. When you expand for small a, of course at a equals 0, this is an equality. And the derivative with respect to a is also an inequality. But the second derivative with respect to a gives an inequality. So you find it, so you literally just expand. So for example, s of r prime is s of r plus a times ds dr plus a squared over 2 times the second derivative. And the other one, the square root of, sorry, s of the square root of r prime. It's longer to work out, but it's s of r plus a over 2 s prime of r plus a squared over 8 s double prime of r minus a squared over 8r times s prime of r plus order a cubed again. So when you make these expansions and put it in here, you find that you could learn that a squared over 4, well, after moving everything to the right-hand side, you find that 0 is equal to bigger than S double prime of R plus 1 over R S prime of R. So all I do is I make this expansion, plug it into the inequality, and cancel the terms of 0 or first order in A, and then divide by A squared. And then we get drop higher order in A. And in order A squared, we get this inequality. And that is 1 over R d by dr of R times ds dr. So we learn that something is, the factor of 1 over R isn't important. We learned that something is monotonic on the RG flow. Oh, sorry. Why is this on an RG flow? We learned that this function of R is a monotonic function. But making the RG flow in a theory at fixed lengths is equivalent to keeping the theory fixed and going to bigger lengths. So R ds dr, being a monotonic function of R, asserts that a certain function is monotonic along the RG flow. And we can find what this function is because in a CFT, we had S of R is C over 3 log of R over epsilon. So R ds dr for a CFT is C over 3. So Cassini and Huerta defined a C function, C of R, which is 3R ds dr. And then they had a C theorem, dc dr equal to or less than 0. So that was the entropic proof of the C theorem, or the entropic version of the C theorem. What's proved is not exactly the same as what Zamolodchikov defined. Zamolodchikov had a different function on RG flows that was similarly monotonic. Any questions on that?
So can you get like more information out about the central charge or bounds on that from this inequality? Or is this
I don't believe you learn more than this from the inequality. I'm not aware anyone's claimed you can extract more.
well, we probably can.
Yeah. So, any other questions? Yes?
We converted the lengths into entropies. I imagine using that formula for a CFT, but
No, that formula is only valid in a CFT. The reason I remind you about it was to motivate the definition. We defined the function C in terms of the entropy. But what motivated the definition is that from our previous work, the formula is true. It agrees with the standard definition of C if we have a CFT. So we already had a definition of C for a CFT, but now we've defined C at any length scale in any theory. The motivation for, if you happen to have a CFT, then this C is independent of the length scale and is the standard C. Otherwise, it's a new definition. Same as Zamolodchikov. Zamolodchikov, there was a standard definition of C. Zamolodchikov defined something more general that he proved was monotonic and agreed with the usual C when you do have a CFT. So a special case of this is that if you have a flow from a CFT in the UV to a different CFT in the IR, the C in the IR is smaller than C in the UV. That's a statement that only involves the standard Cs. Because at each end of the flow, you do have a CFT, and the C we've defined does agree with the standard one for a CFT. Any other questions? I won't really explain the proof in 2 + 1 dimensions in detail, but I guess I'll draw a picture. So again, they looked at the future light cone of a point, and then they took a disk. So the C function is going to be defined in terms of the entropy of a disk. So the disk, you cut the cone by a circle. The disk is the disk that you could fill in there. Then you have a bigger disk to the future. Now, in 2 dimensions, we had this setup. Then we consider 2 intermediate ones. That doesn't work in 3 dimensions. In 3 dimensions, they had to consider a large number of intermediate guys. There's a conic section here, and there's a conic section a little bit over to the right. They filled in the region between the 2 disks with many, many conic sections. And then they worked harder using strong subadditivity many times. So the ideas were the same, but the geometry was more complicated. And I think from what I've explained to you, if you look at the paper, you'll easily be able to understand it. It's based on the same ideas with more complicated geometry. In 4 dimensions, they also had to use what I'm going to explain to you in the process of discussing the ANAC. And incidentally, there's no known proof of the C theorem by any method in 5 or 6 dimensions, even though we now know that there are non-trivial examples of RG flows in 5 and 6 dimensions. Okay, well, if there aren't more questions, then we'll move on and discuss the ANAC.
Is there a reason why the different proofs of C theorems in different dimensions seem very different?
Well, it's not unique that the same theorem can be proved in completely different ways. But one thing I want to tell you is that in 3 dimensions, the entropic, not only is the entropic proof the only known proof, but the entropic statement is the only known statement. In 2 dimensions, there's a C theorem. And in 4 dimensions, the proof that imitates Zamolodchikov's, which was by, I'll tell you who did it when the names come back to my mind. Schwimmer and Komarkovsky, thank you. Okay, there the proof, well, C involves an anomaly coefficient in 4 dimensions. But in odd dimensions, there's no conformal anomaly. So there isn't a statement in terms of an anomaly coefficient. And there isn't a known statement in terms of a correlation function of the stress tensor. I guess you can't completely rule out that there could be such a statement. So the only known statement of the C theorem in 3 dimensions is entropic. So Zamolodchikov's version of the C theorem was positive definite. This is certainly positive definite at CFT, but I'm not sure it's completely obvious that it's positive at a non-CFT. Because of the normal, well, sorry. I'm not going to make an immediate claim. And I think in 3 dimensions, although there is a, well, it's called the F theorem. I think the answer is going to be no for positivity in 3 dimensions. You prove monotonicity on RG flow, but I'm not certain that the thing that's monotonic, as usually defined, is positive. You can always stupidly take the exponential of a real number and make it positive. But the natural definition I don't think is positive. But I might be forgetful. Any other questions? Okay, now we're going to move on to the ANAC, and I remind you that in the ANAC, we'll just be in Minkowski space. Although the same argument would actually work for a null line on the horizon of a Schwarzschild black hole. But to keep it simple, we'll be in Minkowski space. And so I remind you that we have a null geodesic gamma, and it has an affine parameter V. And then we look at the ANAC operator which is the integral dv of tvv. So to make clear what's tvv, tvv is t mu nu dx mu dv times dx nu dv. In a previous lecture, well, first we saw why the ANAC was useful for some applications, although we used it in curved space-time where it hasn't been proved. We're only going to prove it in Minkowski space. But the only thing we said before about the ANAC for a light ray in Minkowski space is that we couldn't disprove it trivially. And the reason we couldn't disprove it is that there's no open set that's space-like separated from a null line, from a null geodesic. Remember, if there's a space-like set, if there's an open set that's space-like separated from a null geodesic, then we could have disproved the ANAC by first proving that the operator can't annihilate the vacuum, and then taking a linear combination of the vacuum and something it can create from the vacuum, and proving that the ANAC operator can't be positive. That doesn't work for the ANAC because there isn't an open set that's space-like separated from a null geodesic. And in fact, it's not hard to see that this operator does annihilate the vacuum. It annihilates the vacuum because we can consider the operator PV. The null ray is contained in a null plane. So we'll take our space-time metric to be minus 2 du dv plus dy perp squared. The y perp are orthogonal coordinates. And then our null ray, let's say, was u equals y perp equals 0. But it's contained in a null plane, which is just defined by u equals 0. Of course, there's a whole family of null lines in that null plane with y perp equals constant. Any constant will give us a null line which is contained in the null plane. Now, we can define an operator PV, which is it generates the translation v going to v plus a constant. And one way to define the operator PV is that it's the integral dv dy perp of tvv. So simply the integral of the ANAC operator over the normal plane. Over the null plane, well, over the normal directions to the null ray inside its plane will give us the generator of the null momentum. PV has the property that it annihilates the vacuum, and PV is strictly positive on all other states. Now, you see, PV, so we're actually going to want to study a smeared version of the ANAC operator. So we let f be a function of the normal directions. And we could have taken this ANAC operator at any constant value of the normal directions y. But instead, we'll smear it and define what I'll call P sub f, which is the integral dv dy perp of f of y perp times tvv. Smearing it is really needed to get, as usual in quantum field theory, smearing is needed to get an honest operator. That's one reason we'll smear. But the other reason is that we'll need to consider the smeared version to make the argument we want to make about monotonicity of relative entropy. So I claim that P sub f is equal to or greater than 0 for all f. That's what we'll prove. And that's equivalent to the ANAC. If the ANAC is true, smearing that positive operator, you get a more general positive operator. If this is true for all f, then taking the limit as f approaches a delta function, we learn that the original ANAC operator is non-negative. Smearing gives a true operator. So it has eigenvalues and eigenvectors. Without smearing, as is usual, you get something that has well-defined matrix elements between suitable states, but it's not an operator. It doesn't have eigenvectors and eigenvalues. So the smeared one is better behaved because it is an operator, and it's the smeared one which will be natural in the argument we want to make. The unsmeared one is more like our friend KR, the one-sided boost operator. It has well-defined matrix elements between suitable states. It doesn't have eigenvectors and eigenvalues. Anyway, going back, so now I wanted to prove that PF annihilates the vacuum. Well, the point is that PF commutes with PV. PV generates a translation of V, but since we're integrating over all V and defining PF, PF commutes with PV. So on that account, PF on the vacuum is a state with PV equals 0. But the only such state is the vacuum. So that would prove that the vacuum must be an eigenstate of PF with some C number eigenvalue, simply because the vacuum is the unique state with PV equals 0. But we can also consider our friend the boost. If there's one, well, in general, no matter how many vacua there are, when we construct a quantum field theory, we pick a vacuum, and we consider all the states obtained by acting on that vacuum by operators. So in the world we're studying, there's only one vacuum. It might be that abstractly, the theory we're studying has other vacua, meaning the same, roughly speaking, that would mean that the same operator algebra has different representations.
So there's never a situation where two vacuums, by acting with some family operator, some like operators then merge?
No.
No.
Well, the closest analog of that is something a little like that can happen in 2 dimensions. You have one vacuum at the right end, one at the left end, and a soliton in between. Today we're not in 2 dimensions, and I should have said that at the beginning. The ANAC is trivial in 2 dimensions, because in 2 dimensions, the ANAC operator is the same as PV. It's just a component of it's just a null component of the momentum, so we know it's positive. So in today's discussion, we're above 2 dimensions because the statement we're proving is trivial in 2 dimensions. So although the answer to your question would lead to some exceptions in 2 dimensions, they're not interesting for us. And it will be important, in a little while, it will again be important that we're above 2 dimensions. So the formula for KV that for K, the boost. Oh, well, I could call it, I've usually just called it K. K was when we introduced the boost operator, we were studying a Rindler wedge, right? And we could study a Rindler wedge today. In fact, if we take the point V equals 0, we could draw a light ray that goes in the opposite direction, and here we'd have our Rindler wedge. In fact, we're going to do something like that in a moment. So we will be interested in the Rindler wedge. So for the usual formula we've used for the boost operator is this. And we've also sometimes gotten an improper operator by taking the integral from 0 to infinity or from minus infinity to 0. But above 2 dimensions, another formula is the integral over the null plane This here we integrate over the null coordinates. So, you see, the boost is a conserved charge, so it is associated to a conserved current. And since it's associated to a conserved current, you can always define the charge by integrating over an initial value surface, the charge density. The null plane is not a proper initial value surface, so that takes some discussion. In 2 dimensions, you could have a massless particle going to the right at the speed of light. It would never pass through the null plane. And therefore, you can't define initial data just on the null plane. But above 2 dimensions, everything will eventually go through the null plane. You could have a massless wave spreading in all directions, but the amplitude to be going exactly in this direction is 0. So with probability 1, all of the wave eventually passes through the null plane. So that means that above 2 dimensions, even though the null plane is not a proper initial value surface, we can use it as one. That means that there's a formula for the boost generator as an integral in the null plane, and that formula is what I've written here. Although it's not important for us, I'll mention that that formula is also correct in 2 dimensions. In 2 dimensions, the general argument would be wrong. There are massless waves that go to the right at the speed of light, but they don't. Oh, sorry. No, sorry. The formula for KV might be wrong. The formula for PV is correct because those waves don't contribute to PV. So at least that formula is true even in 2 dimensions. Anyway, today we're really above 2 dimensions, and therefore we can write formulas for conserved charges just on the null plane. And this is the formula for the boost operator. But actually, for what I was about to say, we don't really need the formula. All we need to know is that the boost operator rescales PF. The boost operator rescales the null plane. And PF is not invariant under scaling of V. There's a TVV with 2 V's, and there's an integral dV with 1 V. So if you rescale V, which is what the boost generator does, that rescales PF. And that shows us that PF can't act on the vacuum by a non-zero multiple. The multiple has to be 0. Any questions so far?
Maybe a quick one. We're considering Minkowski space-time here, but what's the restriction on the operators that we're allowed to write? Because there are the operators on like holographic literature, for example, it's in like a shock wave with negative energy, and then you can violate the annex.
No, you can't violate the Anak in Minkowski space. We're in the process of proving that the Anak is true in Minkowski space. The context is that we're citing quantum field theory in Minkowski space. And in that context, the Anak is a theorem. There are various proofs in literature. I'm giving you the one that's closely related to the methods we've developed. Now, we're going to consider what are called cuts of the null plane. A cut just means that we let V be a function of the normal coordinates. So I have trouble drawing the null plane, but this is meant to be the V direction, and these are the normal coordinates. I'm trying to not specify how many normal coordinates there are, but there's at least one, because we're going to make various statements that are untrue if there are no normal coordinates, and plus the statement we're trying to prove is trivial then. So one cut is the one we've discussed, where V is 0. But a more general cut with E that V is some general function f of y perp. Now, each cut of the normal plane defines a space-time region for a picture that I actually can draw, but a slightly misleading picture because we're in 2 dimensions. By the region associated, so if the cut is at v equals 0, I take all the part of the null plane to the future of v equals 0, and then I take every point in space-time from which a signal would pass through there. I'd call it the domain of dependence, except technically it's not, because you could have a null ray exactly parallel to the null plane that would never reach the null plane. But as I explained above 2 space-time dimensions, that's not important. In practice, a signal will actually never travel precisely at the speed of light exactly parallel to the null plane, because that would imply a wave function that was a delta function. A normalizable signal will never do that, or a finite energy signal will never do that. So a cut defines the region from which a signal will pass through the given region to the future of the cut. Another way to describe it is that starting with the cut, I could go in a space-like direction to the right and define a conventional space-like surface S. And then the region U associated to the cut is just the domain of dependence of S. Now it's an honest domain of dependence. When we just literally take the part of the null plane to the future of the cut, we're cheating slightly in the definition of the domain of dependence. So the space-time region for this cut would be this region here. It's the ordinary domain of dependence for S. It's not quite properly defined as the domain of dependence of this region. Although I have trouble drawing it, I hope you see that that construction makes sense for any wiggly cut of the null plane. We always can go off to the right with a conventional space-like surface and take its domain of dependence. Or alternatively, we can just take all the points from which, if you travel on a future-going curve that isn't that very exceptional one, a null geodesic parallel to the null plane, you'll pass through this cut. So it's a wiggly region. It's a region that you can't simply describe this region by a formula. You can't because, see, near the null plane, its boundary would be marked out by ingoing null geodesics that go to the right. But after a little while, those null geodesics will reach focal points. And it'll be hard to describe exactly what's the boundary of the open set we're trying to talk about once those geodesics are reaching focal points. Still, I hope I've made it obvious to you that for each region to the future of the cut, there is a space-time region associated to it. And another fact which I hope is obvious is that if I have a cut v equals f, and then I have another cut v equals g, where g is bigger than f for all y, then I hope it's obvious that the region UG is contained in the region UF. And if that's true, then it will also be true that the modular operator of the vacuum for the region UF will be equal to or greater than the modular operator of the vacuum for the region UG, because we proved that modular operators increase when you make a region smaller. Or did I write this inequality backwards? I did. Modular operators increase when you make a region smaller, so the modular operator for the smaller region UG is bigger than the modular operator of the larger region UF. We also proved that if one operator is bigger than another, the logarithms obey the same inequality. So we have this statement. And we're going to see that this is the ANAC. The ANAC is precisely the statement that the logarithm of one modular operator is bigger than the logarithm of the other modular operator. Unfortunately, though, when we started talking about the ANAC, I got overconfident that I had plenty of time, and I started going too slowly. Okay. So we're going to want to look at, well, we could start with the conventional Rindler wedge. Defined by v equals 0. So let U be the algebra of the Rindler wedge. Oh, sorry. U is the Rindler wedge itself. And then A of U is the algebra of operators in the Rindler wedge. Now, what we want to do is we're going to calculate what the operator e to the IPF does on an operator in the Rindler wedge. That's very complicated in general, though, because P sub f is not a symmetry. P sub f isn't a conserved charge. So in general, it's hard to say what P sub f does to operators in the Rindler wedge. However, it's easy for operators on the null plane. So what I want to prove is that, you see, if f were a constant, you'd know that e to the IPF acting on an operator at v equal to or greater than 0, e to the minus IPF. This is an operator on the null plane. Well, if f is a constant, it doesn't have to be on the null plane. That would be an operator at v equal to or greater than f. If f is constant, e to the IPF is a symmetry operator. It simply translates v by f. So it would conjugate an operator at non-negative v to an operator at v equal to or greater than f. So I claim this is true also for non-constant f. For operators on the null plane. Well, why is that? Let's take the commutator of PF with an operator on the null plane. I won't keep writing u. It will be 0 throughout this discussion. So if f is constant, this operator would be f times dv of L. Well, that's not an exact formula, and there will be terms proportional to derivatives of f. So I'm about to make an expansion which you can check explicitly in free field theory. In free field theory, you'll find that if f isn't constant, then its commutator with an operator of the null plane will involve the derivative of f times some other operator. And then there will be a term involving the second derivative of f. These are derivatives with respect to the normal coordinates y. Well, that's what f depends on. Times some Oj and so on. But this is a finite series. If O has dimension d, then its derivative has dimension d plus 1. This operator has dimension d, the next one has dimension d minus 1. And since operator dimensions are bounded below by 0, this series will stop after a number of terms that depends only on the dimension of the operator. So that's a finite series. Now, it might not be immediately obvious, but my assertion that e to the IPF conjugates operators at positive v to operators at v bigger than f is a consequence of that. Let me remind you of something you probably learned when you were learning quantum mechanics. When you learned quantum mechanics, you wanted to probably calculate the time evolution of a system, but usually that was too hard. You had a free Hamiltonian and a perturbation. And then you probably wanted to calculate the exponential of this operator in perturbation theory. And the starting point, first term, is just to take v equals 0. But the next term is an integral dt prime of e to the I t minus t prime h0 times v times e to the I t prime h0. And the next term will be a double integral. You'll have free propagation for a while. The perturbation will act. Then you'll have more free propagation. The perturbation acts again, and then you have still more free propagation. I'm sure you've all learned this kind of expansion. Now, in our application, we want to think of the term that doesn't involve derivatives of f as free propagation. That's the part we understand. So the operator undergoes free propagation for a while. Then the perturbation acts and its dimension drops down. Then it undergoes free propagation for longer. Or the perturbation might act again, and then free propagation for still longer. The perturbation can only act finitely many times because that keeps lowering the dimension, and eventually we get to 0. So the total amount of free propagation is the total time interval, even though the perturbation could act different numbers of times. So after we act with e to the I pf, I could call it e to the I t pf, well, I'm interested in t equals 1. After we act with e to the I pf, we always have undergone a total amount of free propagation that by itself would give v to v plus f. But sometimes along the way, the operator dimension got lowered. So after conjugating by this operator, we end up with a local operator that's at the same point we would have been if there had been no perturbation. The effect of the perturbation is that the operator we get there is different, because sometimes along the way its dimension was lowered. So therefore, we learn that e to the I pf on a local operator at v, y perp, and u equals 0 times e to the minus I pf is some other local operator at v plus f, y perp, and u equals 0. So the conjugation maps operators on the null plane to operators at a future point of the null plane with v shifted by f. But the operator changes. The leading dimension term is just the derivative of O as if f were constant. There are all kinds of lower dimension terms I'm not making a claim about. I'm only making a claim about where they are. It's important that the series is a finite series because an infinite expansion in local operators wouldn't really be local anymore. And we wouldn't be able to say where it's localized. You see, if you had an infinite expansion, you might run to something like this. That's an infinite expansion of operators which are each at x equals 0, but the sum is at x equals 1. That can't happen to us here because we have a finite expansion. Now, I've only analyzed operators on the null plane. And I should talk about operators in the whole wiggly region, which is the domain of dependence to the future of the cut. I wish I'd presented this in a way that, I'm going to, so I claim that e to the IPF acting on the algebra of operators in the region U where V is equal to or greater than G, e to the minus IPF, is the algebra of operators in the region where V is equal to or greater than G plus F. Strictly, I've only proved that for operators on the null plane. So I should extend it to discuss operators in the whole region that's the domain of dependence above the cut of the null plane. But I'm going to accept that at the moment and explain to you how to finish the argument to get the ANAC. So we're about to get the ANAC rather suddenly. So if you want to ask a question before we get the ANAC, this is a good time. Yes? Is what? No, it's very important. F is not a constant. G is a function of y perp. G and F are functions of y perp. The operator e to the IPF, roughly speaking, it shifts, roughly speaking, e to the IPF. It maps V to V plus F. So it shifted the position of all operators by F. But as I've explained, that's oversimplified. They're terms proportional to derivatives. But on the operator algebra, it's a true statement. Acting on an operator on the null plane at V bigger than G, it produces an operator on the null plane at V bigger than G plus F. G and F are not constants. So this is a region of the null plane where V is bigger than a function G of the normal directions. Here, V is bigger than a different, actually, function of the normal directions. Now, any other questions? So we've learned that e to the IPF, first it maps the vacuum to itself. That was the first thing we learned. And we've learned that it conjugates the algebra for U, the algebra of the region where V is equal to bigger than G, to the algebra of the region where V is equal to bigger than G plus F. Now, it follows what will happen if we act with e to the IPF on the modular operator of the region where V is bigger than G. To define the modular operator, there are two ingredients, the algebra and the state. Well, I've told you that e to the IPF conjugates one algebra to a different algebra, and it leaves the state invariant. So we'll have to conjugate one modular operator to the other modular operator for the same state. If it mapped the vacuum to some other state, then that other state would come in here. But since it maps the vacuum to the same state, we just get a comparison. We conjugate one modular operator into the other. To understand that statement, all that I'm using is the fact that the modular operator is determined by the algebra and the state. So if you have an operator that leaves the state alone and maps one algebra to the other, it will have to map the modular operator of the first algebra to the modular operator of the second. If you go over the definition of the modular operators, you'll see that was immediate. So, well, let's set G equals 0. Then the region where V is equal to or bigger than G is the Rindler wedge. And the modular operator of the Rindler wedge is the exponential of minus 2 pi times the boost operator, k. So, therefore, the modular operator of the region where V is equal to or bigger than F, this is the modular operator of the vacuum for the region where V is equal to or bigger than F, is e to the IPF times e to the minus 2 pi k times e to the minus IPF. So k was our friend integral what do we get if we conjugate k by e to the IPF? In this particular case, all that happens is that we shift V by F. Generically, we'd get operators of lower dimension, but here there aren't any that can come in. Sorry, I put the plus F in the wrong place. It shifts V to V plus F in the operator, not where V was simply a C number. That leads to a very important minus sign, because it's convenient to change variables from V to V plus F. To remove the V from the operator and then put it in the C number. So when you conjugate k, you get k minus pf. So we find the modular operator for the region to the future of f is e to the minus 2 pi times k minus pf. That's more or less the most general modular operator that people really know how to compute in quantum field theory. There are a few stray exceptions, but that's the most important one we haven't discussed previously. What's that?
It's for the part on the right, really important, your series on the left, where you're talking about these finite series, where is it actually?
If we had an infinite series, we wouldn't have known anything. So we wouldn't have been able to prove. There's anyway a gap in the argument as I've presented it, which I want to fill in. Let me go back to your question when I complete the argument.
I'm just wondering, first of all, how this finiteness is being used
It's being used to show that we can't.
The series truncates. Are we making an assumption
It-
about the discreteness of the spectrum?
No, only that the operator dimensions are bounded below. We started with an operator of finite dimension. Each term in the series has lower and lower dimension.
So
Well,
it would be
well-
no square x.
No, we're at integer steps. Each derivative is an integer step. Okay. So now we can take the logarithms. So log of delta omega at v equals 0, equal to greater than 0, which is minus 2 pi k, and log of delta omega for v equal to bigger than f is minus 2 pi k plus 2 pi pf. And this one is bigger than this one, gives us that pf is positive. The logarithm of the modular operator, so if f is positive, then the region where v is bigger than f is a smaller region than the region where v is non-negative. And as we know, that increases the logarithm of the modular operator. And the difference between the two is 2 pi pf. So this inequality just tells us that 2 pi pf is non-negative if f is non-negative. And that's the ANEC. I do wish, though, that I got into this point 10 minutes ago, which I would have if I hadn't wasted time in the middle of the lecture. Any questions here? Yes?
When you conjugated TBV of 3, you got it to shift by F. I guess B shifted by F, right?
Well, in the argument of TVV, it shifted by f.
But in that conjugation, would T or would other components of T not come in? I mean, this is the tensor, so...
Well, they don't, because TVV has dimension, let's say in 4 dimensions, dimension 4 and spin 2. And there isn't anything else. Well, I kept the first term in the expansion, which was dv of TVV. And then we would have had DIF times some OI. OI would have dimension 4 and spin 2. Well, there aren't any operators that... There aren't any... It also has a transverse index. So O would have to be an operator that has spin 2 in the v direction, spin 1 in the transverse directions, and, for example, in 4 dimensions, dimension 4. There aren't any operators like that. So for the special case of TVV, there was only one term in the series. I should have explained that better. I started worrying about the time. Any other questions? So, if there aren't questions, I want to look more carefully at what we actually proved. The key step was that e to the IPF conjugated operators on the null plane at, let's say, v positive to operators at v equal to or bigger than f. And to answer Herman's question, it was important it was a finite series, because otherwise we wouldn't have learned that the operator was a local operator on the null plane. An infinite sum of local operators can be off the null plane. That's, I don't remember if you were here when I said that, but that's what I explained by writing this power series expansion of the operator O of 1 as an infinite expansion in operators at x equals 0. So if you have an infinite series, you lose control over what you're talking about. However, we didn't study all operators in the Rindler wedge. We only studied the operators on the null plane. So was that enough? First of all, in free field theory, it's trivially enough, because in free field theory, the operator algebra is generated by the free field. The free field on the null plane is well defined. Actually, Herman has invited me to give a talk on I think the first Monday in December, which you're all invited to, where I will discuss what kind of smearing produces an operator. So I won't in detail now explain that smearing of the null plane is enough to make an operator in free field theory, but that will be a special case of what we'll discuss on that later occasion. So in free field theory, the operators on the null plane above the cut actually generate the operator algebra. So there's nothing more to say. But what if we're doing QCD rather than free field theory? In QCD, as we will also learn in that later lecture, there are no honest operators you can make on the null plane above the cut. So for QCD, there's a gap in the argument, and I believe it should be filled as follows. So if we're discussing, say, QCD, we'd have the operator, for example, psi bar psi, or trace of f mu nu squared. Let me just call it O. O is one of these. And we look at O on the region equal to or bigger than 0 above the null plane. Now, if we were allowed to smear O a little bit in time, we could get honest operators that generate the operator algebra. But if we smear it in time off the null plane, we would no longer know what p sub conjugating by e to the IPF does. We can, however, reason as follows. Let A be an honest operator. So, sorry. We had the region where U or V was equal to or bigger than F. And there's a space-like separated region. It's again hard to draw. It's bounded by the part of the null plane where V is less than F, but it goes in the future of that. We could find it by taking a spatial surface that goes to the left from our cut of the null plane and taking its domain of dependence. But anyway, let that region be V. And now consider the operator algebra. The algebra of honest operators, V. It's the algebra associated to V being less than F. Well, I can characterize it by saying that A for V being less than F commutes with local operators on the null plane at V equal to or bigger than F. So, you see, a local operator isn't an honest operator, but it makes sense to say that it commutes with a local operator. It means that, I'll call it A prime. A prime is an operator in V. The left-hand side you can think of as A prime dagger chi times O psi. And the right-hand side. So it's an inequality among two different matrix elements of O. And we agree that local operators have matrix elements, although they're not operators. So it makes sense to say that, an honest operator commutes with a local operator. And since our operator e to the IPF conjugated local operators above a cut of the null plane to local operators above a bigger cut, they have to also conjugate one commutant into the other. So e to the IPF conjugates the algebra at V equal to or bigger less than 0 to the algebra at V equal to or less than F. Once you get this far, you can take the commutant again. If it conjugates this algebra into the smaller algebra, it has to conjugate the commutant of this one, which is the one we want. However, I think I've probably baffled most of you with that argument. It needed more time to explain it properly. So maybe reluctantly, I'll have to spend a few minutes at the beginning Tuesday trying to explain that. Any questions? And then we'll have to call it a day.
What did you use this commutant argument to prove? The same statement?
Well, we had a statement. We had a statement for local operators above the null plane. Okay. Now, that's not an honest operator algebra. So, see, as a notation, A prime is the commutant of A. For any algebra, A prime is the algebra of all operators that commute with A. Let U be a unitary. I'll use the following. If U, A, U inverse equals B, B is another algebra, then U, A prime, U inverse equals B prime. That's an inevitable fact of life. And it therefore follows that U, A double prime, U inverse equals B double prime. What is A double prime? It's the commutant of A prime. Now, I use this principle, but you see, I didn't start with an algebra. I started with an improper set. Local operators on the null plane at V equal to or bigger than F. It's a set of local operators. It's not an algebra. They're not honest operators, and you can't multiply them. In general, you get singularities. But what I called A prime, well, sorry. Let B be S prime. As I said, it does make sense to talk about operators that commute with S. And then B prime is with the S double prime, but S double prime is actually the algebra we want. Honest operators at V equal to or bigger than F. So I made a trick. I knew that U conjugated the set S to another set SF. That's not a statement about algebras. But it trivially follows that U conjugates, if it maps S to SF, it has to map S prime to SF prime. That is a statement about algebras. And then we can do it again, and we get S double prime going to SF double prime. That's still a statement about algebras. But that statement is the one we want. Because an operator that commutes with all operators that commute with the operators in the null plane is going to be an honest operator that has to live in the region we're interested in. I hope that explanation didn't completely baffle everyone, although I would have wanted to explain it more slowly. But we're out of time. So I'll see you Tuesday.